So equilibrium constants are constant, but there are things that can cause them to change, and one of those things is temperature. If you run a reaction at a different temperature, that may affect the equilibrium constant. So oftentimes the temperature will be specified when you're given an equilibrium constant. They'll say the equilibrium constant is 5.3 at 25 degrees Celsius. The 25 doesn't come into the calculation at all. It's just there as sort of the small print. Concentrations for the substances are always in moles per liter, but we normally drop the units here so that the equilibrium constant is unitless. Otherwise, if we kept the units in there, they would all have really crazy units, like molarity squared per liter squared and things like that. And it's not meaningful anyway, so we just drop it. At a particular temperature, the equilibrium constant is always the same. The concentrations can be very, very different. But the relationship between them always gives us the same constant. So let's look at this reaction. We looked at this one before, H2 plus I2 giving us 2HI. Suppose we have a mixture of those two gases, H2 and I2, and we allow it to come to equilibrium at 445 degrees Celsius. The measured equilibrium concentrations are 0.11 molar for the hydrogen and 0.11 molar for the I2, and the HI has a concentration of 0.78 molar. What is the value of the equilibrium constant? So what we're going to do is we're going to write the equilibrium constant expression, and here we have the molarities, the concentrations, so we'll plug them in and do the calculation instead of just writing an equation. So KEQ for this reaction, we have all gases. There's no liquids or solids, so we're going to include everyone. So the concentration of the product, and that's squared because it has a coefficient of 2 in front of it, divided by the concentration of the reactants. The coefficients on each of these is 1, and so the exponent will be 1. So that's the equilibrium constant expression, and we're given the equilibrium concentration. So we know that H2 is 0.11, I2 is 0.11, HI is 0.78. So we'll put 0.78 in for the HI. That needs to be squared. And we'll divide that by 0.11 and 0.11. Now again, be careful on your calculator. Students want to multiply here. If you're going to do that, you have to put parentheses around those guys. So we've got 0.78 squared divided by, open parentheses, 0.11 times 0.11, close the parentheses. And my calculator is giving me a whole bunch of digits. And so I want to think ahead, how many sig figs should my answer have? 2. All of the numbers I was given are 2. So my answer should have 2 significant figures. So I'm going to write down what my calculator shows me, the first 2 significant digits and 2 extras. That's a 0. So there's my significant digit. And so I can round that and say it's 50 with a decimal point, or it's better to say 5.0 times 10 to the 1. That's the value of the equilibrium constant. It does not have a unit. We just drop the units. Some of you have been dropping the units all semester. Now you can be right in dropping the units. Any questions? I didn't have a lot of these graphics, most of them I get from the publisher. They're the same things in the textbooks. But I couldn't find this one in the files they gave me, so I took a picture of it. So this is pretty cheesy, but I wanted to show you this from your book. It's table 15.1. This is that same equation we were just looking at, and we calculated the equilibrium constant, and we found out it was 50, right? So over here, this is the one we just did. Here are the equilibrium concentrations. We plug them in, we get 50. They're being sloppy with the sig figs. What if we started with just the product and none of the reactants? Let it come to equilibrium. This is what we'd end up with. You plug those numbers in, you still get 50. What if we started with equal amounts of all three and let it come to equilibrium? These would be the equilibrium concentrations. You plug those in, still comes out to 50. Let's start with twice as much hydrogen as iodine and no product. This is what you would measure at equilibrium, still comes out to 50. The concentrations of all the reactants and products can change, and they will change, but the equilibrium constant stays the same at a given temperature. Any questions? So let's look at this reaction. We've got a mixture of carbon monoxide and hydrogen, and this can form methanol. This temperature here is just for information. We don't need that in the calculation. Here are the measured equilibrium concentrations. They're just handed to us there. What's the value of the equilibrium constant? Well, we're going to write the expression. So we look at these, and we've got gas, gas, and gas. So we're not going to leave anyone out. The equilibrium constant will equal the concentration of the product divided by the concentration of the reactants multiplied. So we've got carbon monoxide and we've got hydrogen, and the hydrogen has a coefficient of 2, so that's going to be squared. It's just how the equilibrium expression is defined. So then we plug our numbers in, being careful to get them in the right places. So we got 0.151 in the numerator. The carbon monoxide is 0.489, and the hydrogen is 0.146, and that has to be squared. Okay? So again, if you want to multiply down there, you need to put parentheses around the whole denominator. It's not how I do it, but it seems to be what most 3A students would rather do. So we'll do that. 0.151 divided by, let's open parentheses, 0.489 times 0.146 squared. Your calculator should have an x squared button. And you can just press that. And then close the parentheses, and I'm getting 14.486. All of my numbers here had 3 significant figures, so I should keep 3 sig figs. 14.4 would be 3 sig figs, carry 2 extras, and then when I round that I get 14.5. And again, the equilibrium constant does not have any units. Any questions? Yeah.
The square root for both of CO and H2O?
No, only the H2 is squared. So the H2 is squared, the carbon monoxide is not. It's a good question. Because up here, CO has a coefficient of 1. H2 is the only one with a coefficient of 2. So they're independent. I'm kind of curious how they figured out that this relationship of taking the concentrations of the products raised to the powers of their coefficients and dividing by the reactants, how that came out to be a constant. I mean, how many other things did somebody try before they figured that one out, right? Seems kind of random, but there it is. It's great. So we can use the equilibrium constant to calculate the concentrations at equilibrium. So what we've done so far is all very nice, but it's not actually all that useful. What you would want to use this for in an experiment is, okay, I've got this mixture. I know what I started with. I want to know what I'm ending up with, okay? Some of these things can be measured easily, others cannot. So here we have an equation. COF2 is forming CO2 and CF4. Here's our equilibrium constant at 1,000 degrees. There again, it's just for our information, we can assume that this is occurring at that temperature. We're given this information here. Equilibrium concentrations of two of the things and the equilibrium constant, which is just up here, and we're asked to find the other thing. So we write out the equilibrium constant expression, and then we'll note that one of the pieces is missing, and we have the other information. So the equilibrium constant expression, KEQ, it's products over reactants, so CO2 times CF4 divided by COF2, and that one is squared because of this 2. Everybody okay with that? So we're trying to find CO2. Yeah, you could stick the numbers in here and then mess around with it. It's really better to rearrange the letters before you stick the numbers in. So if I want CO2 by itself, I need to get rid of the CF4 and the COF2 squared. So I could do that. I'm going to be dividing by CF4 so that those cancel out. And I'm going to multiply by COF2 squared so those cancel out. If I do that to one side, I have to do it to the other side also, which, I didn't plan ahead here very well, did I? You can also look at this as in terms of ratios or proportions, and anything that's in the denominator over here, you can just move to the top over there. You can take this and just move it down there. Some of you understand how that works. If you don't, just do it this way. So what I end up with here is the CO2 concentration is going to equal the equilibrium constant times COF2 squared divided by CF4. That's algebra, rearranging an equation. In mastering chemistry, what they do, because writing all these chemical formulas gets really tedious, they'll say, call this A, call that B, and call that C. And then they'll ask you to rearrange it and do stuff with it. So they're just subbing in a single letter for these complicated formulas. Okay, so now we've got these three things, and those are all on this side, and so we can plug the numbers in. We've got KEQ is 2.00. The concentration of COF2 is 0.255, and that's squared. I noticed when I was grading experiment 13 yesterday, especially on the pre-lab, I don't know what happened. There must have been something in the air. A lot of you copied numbers down incorrectly. Like it was given this and you'd write 0.225 and do the calculation with that. Or you do this as 1.118. I don't know what happened, but a whole bunch of people did a lot of different random mistakes like that. It was very, very weird. So just, double check, make sure that you're writing down the same number. And then down in the bottom, CF4 is 0.118. So this tells me then that my CO2 concentration should be 2 times 0.255 squared divided by 0.118. Make sure your calculator's giving you the same answer that I'm getting. We should have 3 sig figs here. So that would be 3 significant figures. I'm going to round that. And what unit do I slap on here? None? Well, KEQ doesn't have a unit. The concentrations have units. Oops. So it should be molarity, moles per liter. What was your question? Nothing? Any questions? Here's another example. So diatomic iodine decomposes at high temperatures to form iodine atoms according to this reaction. Very simple reaction here, just one reactant and one product. In an equilibrium mixture, the concentration of I2 is 0.10 molar. What is the equilibrium concentration of I? I2 and I are different things. Here we've got I2, and there we've got 2I. I know, right? Sounds like a tongue twister or something. Well, let's write the equilibrium expression. So KEQ is equal to the concentration of the product. It has a coefficient of 2, so we're going to square that, divided by the concentration of the reactant. So they told us the concentration of I2 equals 0.10 molar. Here we have KEQ, and what are they asking us? What is I? So we're looking for I. So this is our equation. We need to rearrange this and get I by itself. Isn't that cool? So we want to get I by itself, so we need to get rid of the I2. So we'll multiply both sides by I2. So the I2s on this side cancel out. Now we've got the concentration of iodide atoms squared is equal to the equilibrium constant times the concentration of I2. I don't want I squared. I want I. How do I get it? Square root. The funny thing, right? Draw it in the air. I know what you mean. If we take the square root of both sides, we can do anything to this equation as long as we're fair about it and do the same thing to both sides. So I'm going to take the square root of that side and the square root of this side. When I take the square root of something that is squared, those things cancel out. So that makes the square go away. So the concentration of iodine atoms is equal to the square root of the equilibrium constant times I2 concentration. So the square root of, and in here we've got the equilibrium constant, 0.011, and we've got the I2 concentration, which is 0.10, and we're taking the square root of the whole thing. So the buttons you push in your calculator will depend on the type of logic that your calculator uses. I'm using the TI-36X Pro, and so on this one what I do is I do the square root symbol first, and then I do 0.011 times 0.1 and press enter, and I get my answer. We should have 2 sig figs here, so 0.03316 or 0.033. That's a concentration. Concentrations in these problems are always expressed in moles per liter. You may need to do different things on your calculator to get the square root. If you need help with that, please ask me in lab, okay? They're all different. It's very confusing.